So our next session will be by Professor Raghavendra Gupta of IIT Guwahati. He is a faculty in the Chemical Engineering Department of IIT Guwahati, and the session will be on turbulent flows. So over to you, Professor Raghavendra.
Thank you, Payal, for the introduction. I will try to discuss the basic features of turbulent flows and some glimpses of how the turbulent flows are modeled, or what are the problems in modeling turbulent flows and how those problems are tackled. So, so to start with, I have a picture here of turbulent flow behind a boat wake. So when you are riding a boat and you see that the wakes are being left behind and the flow is generally turbulent, right? So all of us have seen turbulent flows around us. Most of the flows that are occurring in industry, until it is micro scale flows, they are turbulent in nature. And the first thing probably we use, or first parameter we use to identify if the flow is turbulent or laminar, we look at the Reynolds number. So for example, all of us would have studied in undergraduate that the flow is becoming, or flow becomes turbulent in general for a pipe flow at about Reynolds number 2000, 2100, 2300. For boundary layer on a flat plate, when we talk about, so the typical value when this transition for laminar to turbulent occurs, it's about 5 into 10 raised to the power 5, or for flow over a sphere, the Reynolds number is of about 3 into 10 raised to the power 5. Now, these are just typical values, but depending on how smooth the surface on which the flow is happening, and how calm the environment is, for example, the pump from which the flow is happening, the surroundings, etc., then these transition Reynolds number can change, and people have shown that the flow can be laminar in a pipe flow for a Reynolds number, for a very high Reynolds number of the order of 10 raised to the power 5 even, when they have taken special care that there are no disturbances present in the surroundings. So how do we characterize that the flow is turbulent? So turbulent, as the name suggests, the turbulent flows are characterized by the random three-dimensional fluctuations. So the randomness is that, as the name suggests, that when you say turbulent, or not necessarily with respect to the flows, when you use the term turbulent, it might mean chaos or randomness. So the same is true with turbulent flows, that they are characterized by the random fluctuations in the flow, and these fluctuations are generally three-dimensional. So the fluctuations in what? The fluctuations in velocity and pressure. So for example, if you measure the velocity at a particular point in a turbulent flow, you are going to get a velocity like this, where you can see that the flow is not necessarily periodic. So turbulent flows are not generally periodic. The behavior is completely random. So randomness is what defines turbulence. And then you have three-dimensional fluctuations. And we all know that laminar flow, where the name itself suggests the flow occurs in laminage, which means in parallel layers, whereas turbulent flows, where the flow can occur across the laminage. So, and in laminar flow, as the Reynolds number is the ratio of inertial forces and viscous forces. So lower the Reynolds number, that means dominant the viscous forces are. So at low Reynolds number, viscous forces are dominant and the flow is laminar, because the fluctuations that occur in turbulent flow or because of inertia, they die down because of the viscous effects. But when inertial effects become dominant and the Reynolds number become high, then it is not possible that all the fluctuations die down and you see the flow to be turbulent, characterized by random fluctuations. Okay, so there is another picture of turbulent flows which we all see. The smoke, say for example, the smoke from a incense stick. So the turbulence is characterized by randomness, then diffusivity. So for example, I am a chemical engineer, and we are concerned with oftentimes with mixing. We want to do reactions in a reactor, and in order that to happen, two reactants need to be mixed first. So that mixing occurs, or it can occur because of diffusion. Now, diffusion can happen because of molecular diffusion. So molecular diffusion is that the molecules are moving around randomly, but this diffusion is very slow, especially in liquids. So in turbulent flows, because there are a lot of vortices, a lot of eddies, and these eddies can range from from the smallest scale to a large number to a very large scale. So the largest scale can be the scale of your problem. So for example, if you are considering the flow in a room, the largest scale can be the dimension of the room itself, and the smallest scale, what we call Kolmogorov length scale, so or the scales at which these the fluctuations are dissipated by the viscous motion. So another very important property of turbulent flow is diffusivity, which can be used, for example, if you want to do heat transfer, not only reactions, but if you want to do heat transfer, you get a lot of mixing because of the inherent diffusivity present in turbulent flows. Of course, they are characterized by the large Reynolds number, and as I said earlier, that the large Reynolds number means that the viscous effects are not so important or are dominated by the inertial effects. Then you have three-dimensional vorticity fluctuations. So it suggests that in turbulent flows, the vorticity effect or the vortices are present, and these vortices, there are fluctuations in vorticity, and these vortices are three-dimensional. So turbulent flow is three-dimensional in nature, and then the energy that is present, because there are fluctuations in turbulent flow, and these fluctuations, they eventually need to die, or they eventually die down. So there has to be a continuous source of energy which causes the fluctuations in the flow, and these fluctuations cascading happens. So these fluctuations move, or the energy in the fluctuations is transferred from the largest scale, largest length scale, to the smallest length scale. So that happens, and it is called energy cascading. And that the smallest length scale, because as the scale becomes smaller and smaller, viscous effect can become important. So at the smallest length scale, the energy is dissipated by the viscous effects, and this energy is converted to thermal energy. Now, of course, so we said that there are number of scales present in turbulent flows, but even the smallest length scale that is present in turbulent flows, the smallest length scale is bigger than the molecular length scale. So we can treat the flow to be continuum. I hope that everybody knows what is continuum, because when we model fluid flow, the entire structure that you are modeling in OpenFOAM, you solve Navier-Stokes equations, the momentum conservation equation and mass conservation equation. all these are differential equations, and you can model a phenomena in using differential equations only when the continuum assumption is valid, only when you can treat the velocity fields to be continuous, density fields to be continuous, pressure fields to be continuous, and that is possible only when the length scale of the problem is sufficiently large than a typical length scale, which represent the intermolecular distance. In gases, this intermolecular distance can be a mean free path, and in liquids, the average molecular distance. So it is still continuum. Now, these eddies can have a wide range of time and length scales. So as I said, that the length scales or the size of the eddies, they will be the largest size that will be limited by the dimension of the system. How big? So if you're talking about the pipe, the diameter of the pipe can be your largest eddy size. And then this energy is being transferred from larger eddies to the smaller eddies, which we call energy cascading. And this is this famous quote you see in many turbulence books, that big whirls means the vortices, they have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity in the molecular sense. So this represents that there are bigger vortices. From there, the energy or the turbulent kinetic energy is transferred to the smaller vortices and down to the smallest scale where the energy is dissipated by viscosity. So when the eddies become smaller, and at such the smallest scale, the viscous effects are important, and this kinetic energy is converted to heat. So this gentleman, Kolmogorov, who provided a lot of insight on turbulence by simple dimensional arguments and scaling arguments. So he suggested that the size of smallest eddies, or the length scale, velocity scale, and time scales, all the things. So the first size means the length scale of the smallest eddy. So we know from here that the largest eddy can be the size of your system, and then the smallest eddy, he suggested that there can be a universal correlation for the smallest eddies that will depend on the rate of energy dissipation. So energy dissipation, energy means the turbulent kinetic energy, which is basically in terms of fluctuations. So the rate of energy dissipation and fluid properties. So which is because the viscous effects will depend on mu and rho, or if you want to write it in terms of kinematic viscosity, then nu, which is mu over rho. So by just simply looking at dimensional arguments, the turbulent kinetic energy, which is, I will have the definition in the later slides, but let me just write here, half sigma u I dash squared. So turbulent kinetic energy is basically ui, vi, and wi, or u1, u2, u3. They are the fluctuations. So the square of that divided by 2 represents turbulent kinetic energy. So depending on or using turbulent kinetic energy and the rate of this kinetic energy dissipation. So the unit of K is meter square per second square, as you can see from this expression. So it should actually be called a specific turbulent kinetic energy, and epsilon represents the rate of dissipation of turbulent kinetic energy. So the kinetic energy per unit time, which is meter square per second square, meter square per second square divided by second. So its unit is meter square per second cube. So you can construct length scale, velocity scale, and time scale using simple dimensional arguments or the Buckingham pi theorem, which all of you would have studied in your undergraduate course on fluid mechanics. So this gives you an idea about the smallest length scale that is present in turbulent flows. So if you want to model from the modeling perspective, you will need to, because these scales can give you an idea that what is the smallest length scale, what is the smallest time scale that is going to be present in your flow. So you would like your mass to be smallest possible so that all these length scales are captured. So you can have an idea or you can calculate what L is going to be. Of course, you need to have some idea about what is epsilon, what is K, the fluctuations, etc. If you know that, then you will have an idea that what kind of mass or what size of mass is required. So typically those values will be very small. And that is the reason, because as you would have learned, that your solution will be as accurate if you are able to capture all the gradients. And to capture all the gradients, your mass needs to be sufficiently small in the regions where the gradients are large. Okay, so so you need to have a very refined mass, plus when you are resolving all the time scale, your time step also needs to be very, very small. And that makes modeling turbulence directly or solving the conservation equations directly using, even with today's computational power that is at our disposal, it becomes very difficult to solve these Navier-Stokes equations for turbulent flows accurately so that you can capture all the length and velocity scales and time scales. So that is why you need to go, or you need to do develop some models which are generally heuristic models. So what can be done is one can decompose the velocity in mean and fluctuating components. So as you can see here, that the velocity, let us say u component of velocity with time, it is randomly moving. But if one can average this velocity over a sufficiently long time. So the averaging, there are different averaging that can be done. If it is homogeneous turbulence, homogeneous meaning that it is same in all directions, then one can even use space averaging. If it is, or one can do time averaging, and one can even do the ensemble averaging for state, or ensemble averaging is that averaging over a large number of samples. So this averaging is done over a sufficiently long period of time so that your time average is independent of your t average. So you are going to get, if you average over a sufficiently long period of time, then you get a mean velocity which is represented here using u bar. So you can decompose your velocity in terms of u bar and u dash. So u dash is the fluctuating component. So for example, if I look at this particular time, this is my u dash, or the fluctuating component, and you have velocity u bar. Similarly, you can decompose v component of velocity v bar and v dash, and the z component of velocity w in w bar and w dash. And the same can be done for pressure. So you can basically decompose the velocity field and pressure field in mean and fluctuating components, and it is called Reynolds decomposition. Now, this averaging can be done over or should be done over a sufficiently long time interval so that the fluctuations are averaged out. So if you average fluctuations, or if you write, say, if you average fluctuations, this value is going to be 0, because over a long period of time, the sum of fluctuations will be 0, from you can see from this relationship. But this averaging time scale will be sufficiently small from the time scale that is involved in your process. What is your flow time scale? Okay. Now, so U bar can still be a function of time. That means your mean velocity in this case can be a time dependent velocity. Sometimes it might be steady, but if the flow is, if you think that your flow is time dependent, then you can have a mean velocity which is time dependent plus fluctuations. Okay. So as I discussed in the previous slide, that the fluctuations, they can be represented, because if you average fluctuations over time, then you are going to get their value to be 0. So in place of averaging fluctuations, what is done is you take u dash square plus v dash square plus w dash square. So you take the squares of u dash, v dash, and w dash, and they are represented half of them, half of sum of fluctuations, or square of fluctuations, you call turbulent kinetic energy. Okay, again, so I would like to emphasize here that the unit of turbulent kinetic energy, even though we call it kinetic energy, the unit is not meter square per second square. So it is basically specific turbulent kinetic energy, or the kinetic energy of the fluctuations per unit density. Now, if you use those decompositions and write down in the Navier-Stokes equation. So if in your Navier-Stokes and continuity equation, if you substitute, for example, your for an incompressible flow, your continuity equation is del dot u is equal to 0. Now, if you substitute in place of u bar plus u dash, then okay, so del dot u is equal to 0, and you substitute u by u bar plus u dash, so mean component of velocity and the fluctuating component of velocity. And when you do that for the continuity and momentum equation, what you end up with is, so when you average the continuity and momentum equations, you are going to get similar looking equations. Del dot v bar is equal to 0. So it is continuity equation, but now in place of v, you have v bar, which represents the mean velocity. Similarly, you will get a momentum equation where you have the usual acceleration term. This is your time dependent or unsteady term, and then you have convective term, pressure gradient. So in all these terms, what you have is mean velocity in place of the velocity, or similarly mean pressure here. Then you have viscous term and the body force term. Now there is one extra term that you end up with, which is this del dot minus rho v dash v dash. So v dash is basically, it represents the fluctuating velocity vectors. So this is an additional term. Now, when you are trying to solve a flow problem for an incompressible isothermal Newtonian flow, you have two unknowns and two equations. Your unknowns are velocity vector and pressure. So you want to solve for velocity field and pressure field, and you have two equations, continuity and momentum equation. Now, when you are when you have done the averaging, because in general, if you are an engineering student, if you are trying to solve some engineering problem, even if the flow is turbulent, your interest is in the mean flow. So if you will be fine if you can find out the mean velocity and mean pressure field. Now, we have been able to convert using Reynolds decomposition and then averaging. So these equations, after averaging, they are called Reynolds average equations, or RANS, Reynolds averaged Navier-Stokes equations. But the problem now is that we have, apart from V bar and P bar, we have another unknown, which is minus rho V dash V dash. So we do not know this, what is, how we can find out, because this is also unknown for us. So we have more number of unknowns than the number of equations. So the system of equations is not closed. Okay, so this is generally known as closure problem of turbulence. Now, if you look at this term, rho V dash, and so basically it is rho into V square, or rho into velocity, which will give you a unit of pressure or unit of stress. So in analogy with this, it is called Reynolds stress, because in a way it is analogous to viscous stresses or the viscous fluctuations, so or the molecular fluctuations. So it, in analogy with this, it is called stress and Reynolds stress, so, or turbulent stress sometimes. And it is a tensor because you have three fluctuating components and you have their product. So you can have rho U dash, rho U dash V dash, rho U dash W dash, and so on. So you can have 9 components. And this term represents the fluctuations on the mean flow. So if you look at the system of equations, what this term is representing, that the mean velocity field, how is it being affected by the fluctuations, that is being represented by this term, which we call Reynolds stress. And now our task at hand is to model this Reynolds stress. So now we have additional unknown, rho V dash V dash. And this system of equations, as I said earlier, that it is not closed because we have more unknowns than the equations that are available to us. So this is what is called closure problem of turbulence. And that is why we need to develop turbulence models, which can represent, either you can have a transport equation which is for Reynolds stress, or you can represent this Reynolds stress in terms of mean flow in its gradient, which is what we are going to discuss today. So there was one hypothesis or one assumption that was put forward, that this Reynolds stress, in analogy with molecular or kinetic theory of gases, where we get the concept of molecular viscosity, one can represent the Reynolds stress tensor in terms of a viscosity, which is called turbulent viscosity or eddy viscosity or turbulent eddy viscosity, and the velocity gradients, which is, say if you are talking about in xy plane, then tau xy, also tau xy here is only Reynolds stress. So Reynolds stress tau xyr is equal to mu t into du by dy. So this Reynolds stress can be represented as the product of eddy viscosity and mean strain rate tensor. So when you write this completely, then you will get strain rate tensor, which is Sij here. So if you write this in 3 dimensions, and it is convenient to write in index notations, so I can write this minus rho ui dash into uj dash is equal to 2 mu t, where mu t is the turbulent viscosity, into Sij, where Sij is the strain rate tensor. -2 by 3 rho k, where k is the turbulent kinetic energy and delta ij is the Kronecker delta, which is equal to 1 if I is equal to j and 0 otherwise. Right. So this represents the complete definition of Bussin's hypothesis, that you can represent Reynolds stress in terms of Sij and mu t, and of course this turbulent kinetic energy. Now what we have done, that in place of Reynolds stress, we have represented Reynolds stress in terms of a kinetic energy and the gradients of or the derivatives along the space of mean velocity. Sij is in terms of mean velocity. So Sij you can write half of dou ui over dou xj plus dou of uj over dou xi. Okay, so that is your strain rate tensor, and these are in terms of mean velocity. Now we have got rid of, or we can represent the Reynolds stress in terms of mean velocity gradients and turbulent viscosity. But now this turbulent or eddy viscosity, we need to represent in some of the turbulent properties. So this is what, when you represent in terms of turbulent kinetic energy and epsilon, which is, if you remember, it was the rate of dissipation of turbulent kinetic energy. Then it is called K epsilon model. And when it is represented in terms of K and omega, so K is again turbulent kinetic energy, and omega is the specific rate of dissipation of turbulent kinetic energy. So a specific rate of dissipation here means that the rate of dissipation of turbulent kinetic energy divided by turbulent kinetic energy. So the unit of omega is second raised to the power -1. So again, we can look at what these three terms mean: K, epsilon, and omega. So K, we have already seen that it is turbulent kinetic energy represented by half U dash square plus V dash square plus W dash square, where U dash, V dash, W dash are fluctuations, and the unit is meter square per second square. Epsilon, which is rate of dissipation of turbulent kinetic energy per unit mass. So the unit will be turbulent kinetic energy per unit time, which is meter square second raised to the power -3. Now this epsilon can be represented by this expression, where nu is the molecular kinematic viscosity, or mu over rho, multiplied by gradients of fluctuation. So dou ui dash by dou xk. So this term represents the dissipation of turbulent kinetic energy. And remember, this dissipation happens because of the molecular viscosity. So that is why we have nu in front of this term. Now omega, which is called specific dissipation rate, or dissipation rate per unit turbulent kinetic energy. So when you divide this turbulent kinetic energy dissipation divide by turbulent kinetic energy, then you are going to get second inverse as your unit. Okay. So you can say that this omega also represents some mean frequency of turbulence. Probably that is why it is given this the symbol to represent that, because omega, which is generally used to represent some frequency or second inverse. It can also be thought of a kind of 1 over omega can be a time scale, and this is the time scale at which dissipation of K occurs. Or It can be also thought of the rate of dissipation, because this rate of dissipation is happening from the largest stage to smaller stages. So this is rate of transfer of turbulent kinetic energy to the smallest stage. Okay. So then there are different models. Now, this turbulent kinetic energy, if you go back, what we have done is we have represented the Reynolds stress in terms of turbulent viscosity and mean strain rate tensor. Now, we need to represent mu t, or we need to find out mu t, because unlike molecular viscosity, it is not property of the fluid. It is property of the flow. And flow means it is property of the turbulent flow. So it depends on the turbulent kinetic energy and some representation of dissipation of turbulent kinetic energy. So in K epsilon model, we have this, that we can write mu t in terms of K and epsilon, and of course rho. So if you do a dimensional analysis, you can easily see that mu t will be rho K square by epsilon. So you get turbulent kinetic energy is proportional to rho K square by epsilon, and then you put a constant together. So then you have equality sign, that mu t is equal to rho C mu K squared by epsilon. Now, how do we find out K and epsilon? Initially, when your flow is entering, probably you have some idea about what kind of fluctuations are present, or what is the turbulent intensity. So you can put in some values of K and epsilon. And then how this K and epsilon is being transported. People have developed, or one can derive the transport equations for K and epsilon directly from Navier-Stokes equation, taking its different momentum. But then again, you will have some unknowns, so which needs to be closed. So to cut matter short, what one can do is, or people have developed different transport equations for K and epsilon for the transport of turbulent kinetic energy and turbulent rate of dissipation of turbulent kinetic energy. So the first equation is for K, and if you look at the first or the left-hand side, is exactly what you see for your, say, moment, the transfer of energy or specific enthalpy, or the transfer of, or the transport of momentum, or transport of concentration. So that is your material derivative term. This term basically represents the diffusion of turbulent kinetic energy. So what you see here, apart from mu is basically which represent the diffusion of turbulent kinetic energy because of molecular transport, and mu t over sigma k, it represents the diffusion of turbulent kinetic energy because of the turbulent fluctuations. Then you have another term pk, which represents the production of turbulent kinetic energy, and rho epsilon represents the dissipation of turbulent kinetic energy. Now this P term Pk, basically it comes from the interaction of the fluctuations. So you see the fluctuations, which is basically Reynolds stress multiplied by the mean strain rate tensor. So this, as we saw our hypothesis, so it can be represented as mu t s square. So you have both of these can come as source term in your system of equations. So basically a material derivative term, or transient term and convective term, diffusive term, and then you have a source term. Similarly, you have a transport of epsilon. So epsilon basically represent the rate of dissipation of turbulent kinetic energy. Again, you have unsteady term, then you have convective term, diffusive term, and then production of dissipation and dissipation of dissipation. So basically, to cut matter short, what you can say, there is a transport equation for K, there is a transport equation for epsilon. And so this K epsilon equation is generally useful, or it can model correctly the free shear layer flows. So you have where there are no wall bounded flows. And the other condition is that pressure gradients are relatively small. It does not perform so well for wall bounded and internal flows, except when mean pressure gradients of flow are small. And it does not perform well in any case when there are large adverse pressure gradients. So one need to know that what are the limitations of the model. Then there is another model which is called K omega model. So using same dimensionless arguments, one can write mu t in terms of K and omega, so rho K by omega. And then again, a transport equation for K and a transport equation for omega. You have all these three terms, same, unsteady, convective, and diffusive, and then production of turbulent kinetic energy and dissipation. Sk basically represents that if there is some generation of turbulent kinetic energy, and you may or may not have it. Okay. So this K omega model is generally found to be quite accurate for wall bounded flows where you will have boundary layers. So it is very accurate for boundary layers, and the pressure gradients, they might be favorable or adverse. But it has problem, or it is sensitive to free stream boundary conditions. So you have K epsilon model, which is good in free shear flows, whereas the K omega model, which is good in near wall flows. So what people have done, they have done blending of the two, that if it is near wall, then one can use K omega model, and if it is in the free stream, then one can use K epsilon model. So again, the hybrid of two, or the models which are hybrid of two, have come up, and there are a number of variations of these two equation models. They are used. They have become over time workhorse for turbulent flow modeling, especially in industry. Of course, apart from that, you have LES and DNS models. So when it comes to near the wall, if you look at the velocity profile for turbulent flows in general, it might be internal flow or external flow. This is the typical velocity profile, or what you have that near the wall, what you have on the x-axis is a non-dimensional term, which is kind of a Reynolds number, and is called y plus. So y u tau over nu, where u tau is basically a velocity which is represented in terms of tau w over mu squared root, and it is called friction velocity. So y u tau over nu is the kinematic viscosity. And at the y scale, you have u plus, so mean velocity divided by this friction velocity. So the viscous sublayer, where the viscous effects near the wall, viscous effects become important. And then at the center, your velocity profile, what is there for in the outermost layer, whatever profile you had. So this is for a pi flow, so that is why a power law profile, and pi flow, you might know that 1/7 power law is typically used. And then you have a buffer layer or overlap layer, where which is basically connecting to that the transition happens. So when you want, one need to take into account that what is going to happen at the viscous sublayer, and then two approaches, because if you look at K epsilon model, it is not so good near the walls, and and K omega model can model accurately all the way down to the wall. So there are different near wall treatment approaches that are used. So two different approaches. One is that different wall functions have been developed. So in such cases, the viscous sublayer and buffer regions are not resolved. So that means your mass is not defined near the wall. It is such that the y plus value is more than 30. So you are not modeling this viscous sublayer and overlap layer, and in place of model, a velocity profile is provided at the wall using, and these functions are called wall functions. Another approach is near wall model approach. So where you take care that you are modeling the near wall region so that you are actually your mass is sufficiently refined. So your y plus is of the order of 1. So if you take the first cell height, which as y, and you calculate y plus, then your y plus should be 1 or so, or even less than that, so that you will be able to capture viscous sublayer and buffer layer or overlap layer in your modeling. So one need to take into account that what kind of near wall treatment you are using in your simulations. So if I summarize that what is done in turbulence modeling, especially, or I have only talked about two equation models here. So one can decompose the velocity using Reynolds decomposition in a mean and a fluctuating velocity component. And then one can average the equations, the Reynolds averaging, and then this averaging can be over time, space, or ensemble averaging. So by averaging, you get what you get is Reynolds average, Navier-Stokes or RANS equations. And this gives an additional term in momentum equation, which is called Reynolds stress. And this Reynolds stress needs to be represented in terms of turbulent properties of the flow and the mean velocity. So this is done using Boussinesq hypothesis, where Reynolds stress is represented in terms of eddy viscosity and strain rate of mean velocity or mean strain rate. Then what do you need to do? You need to represent eddy viscosity in terms of turbulent properties. And when you take K and epsilon as turbulent properties, then you call it K epsilon model. When you take K and omega as turbulent properties, then you call it K omega model. So then for you need to solve transport equations for K and epsilon in K epsilon model, and transport equations for K and omega in K omega model. So I think that is what I had, and hopefully it helped. So I will be happy to answer questions if you have any.
Sir, can you explain Boussinesq hypothesis?
So Boussinesq hypothesis is basically, so if you look at what is this tau xy h, it's I have just represented it in terms of tau. It is Reynolds stress. So when you represent Reynolds, you remember Newton's law of viscosity, which tells that the shear stress is equal to viscosity or dynamic viscosity multiplied by gradient of velocity, right? So along the same lines, what is done is Reynolds stress tensor or the Reynolds stress is represented as multiplication or the product of mu t, which is turbulent viscosity, and the gradient of mean velocity. So du by dy multiplied by a viscosity or a viscosity like term which represents the turbulent diffusion, right? So that is what is called Boussinesq hypothesis or Boussinesq assumption.
Sir, turbulent viscosity, we can say turbulent viscosity is a volumetric viscosity because turbulent effect is a volumetric effect or three-dimensional effect.
Yeah, so it is three-dimensional effect, but what do you mean by volumetric viscosity?
Volumetric viscosity means it affects the volume of the infinitesimal element. When we say dynamic viscosity, it is only related to the what is the moment transfer from first layer to second layer or layer to layer. But when we say volumetric viscosity, it refers to volumetric effect on the elements.
Probably you could say so, but I think even if you talk about molecular viscosity, you can have say a viscosity which is non-isotropic. Then you will have layers along x direction, layers along y direction. So there also molecular viscosity will be similar. So turbulent viscosity is actually a flow property, and it is just that one need to represent it in some terms of turbulent property. So you represent in terms of k and epsilon. So I would not divulge too much into that it is a surface phenomena and it is a volumetric phenomena, because ultimately what you again said that it is an infinitesimal volume. So I don't
Yes, sir.
see any merit that how we can benefit by saying it volumetric viscosity.
Okay, sir.
Sir, could you explain the near wall turbulence modeling, like why y plus has to be 1? I did not understand that.
Right. So basically, there can be two approaches. One is, there are two approaches that are being used. One is what is called wall function approach. So wall function approach means that you see this velocity, this graph represents the velocity profile near the wall. Now, you have viscous layer and overlap layer where the viscous effects are important, and then outer layer where the viscous effects are not so important. So one can model this, one can do first approach. In the first approach, one can have his or her the first element size so big that all this is coming into first cell. So the your cell is first cell is somewhere here, so that your y plus is greater than 30. That means viscous sublayer and overlap layer you are not modeling, and in place of modeling you suggest that there is, because this is an universal law, so one can use wall functions, or one can input in your model, you can code such that a velocity profile is defined at the wall in this cell. Okay, so that is your wall function approach. Now, if you want to resolve, no, you want to model it, then you need to have your mass so refined that you can capture, you can resolve a viscous sublayer. If there are no wall functions built in your mathematical model, then you need to refine your grid such that you can capture this phenomenon. Because if your mass is so big, let us say if in near wall model approach, if your mass or first cell height is like this, then you will not be able to resolve viscous sublayer. You are not going to find out the gradients in the viscous sublayer, and then overlap layer where the gradients, or where you have a log law coming into picture. So in order to resolve that, in order to capture those gradients, your mass should be sufficiently refined. So your mass should be refined. So if you look at, I think somewhere that y plus is equal to 5 is where you have viscous sublayer. So if you want to resolve this viscous sublayer, then you should have few elements. So typically, say 5-6 elements, if you have there, then you will be able to resolve viscous sublayer. So that is why I said that you should have y plus is equal to 1 if you want to model or if you want to capture the phenomena using your simulations. Of course, it depends on what model you are using or what is built in the code which you are using for near wall treatment. So probably take home message is that when you are modeling turbulent flow, you need to look at that how the near wall treatment is being done in the mathematical model or the turbulent model that you are using. I hope this answers your question.
Yes, sir. Thank you, sir. And one more follow-up question. So then if the first cell, like if it is very refined, is there any restriction on the like upper cell, the second, third? Can it be bigger? Like
yeah, you can change, but you should change it gradually. So typically you will take the ratio of first cell height and second cell height, say about 1.1 or 1.2. So because gradually you will change this, so there are not sudden changes. And of course, if you are capturing and then first cell height is y plus is equal to 1 and then second cell is quite big, then again you will have only 2 cells in the viscous sublayer. So typically you start increasing the size, but at the same time make sure that you have 3, 4 or 5 cells so that you capture the viscous sublayer. Of course, the viscous sublayer, I think if you look at the profile, it is u plus is equal to y plus. Okay, so it is almost linear velocity profile. It does not appear to be linear here because this is log scale. Right. Again, when you go to overlap layer, it is logarithmic phenomena. So again, the gradients are going to be large. So again, you should have sufficient resolution in this region also, so that you are capturing the gradient here. Because the way you capture if these the profile here is captured accurately, then only probably you will have the mean flow profile and mean flow properties captured correctly.
Sir, in OpenFOAM, this near wall modeling is dependent on the solver or grid size?
It will depend on, I am not sure actually, because I don't use OpenFOAM heavily. So I am also a learner of OpenFOAM like you guys, and I have not done any turbulence modeling using OpenFOAM. So probably I will not be able to answer that question. I will have to look at their help and then see. So what you could do, you can look at the literature where they have modeled K epsilon or K omega or any other model, and see what is the near wall treatment.
Okay, thank you, sir. Sir, in a K epsilon model, initially in OpenFOAM, we are supposed to initialize some random value for K and epsilon. So it's a function of velocity. So when there is inlet and outlet, we can assume some velocity, but there might be some cases where there is no inlet and outlet, like we are just simulating a domain. So in that case, how to initialize this K and epsilon value?
Yeah, so you can use the same thing what you are using when there is inlet and outlet, right? Even if you have inlet and outlet, you need to initialize the K and epsilon values in the entire domain, right? So generally, epsilon can be represented in terms of turbulent length scale. So and from the turbulent length scale, you can represent turbulent length scale in terms of K and epsilon. So K, typically you can take 3 to 5%. The fluctuations or fluctuating velocity is typically, you can initially assume that it is 3 to 5% of your flow. So from that, you can calculate the initial turbulent kinetic energy. And then you have a length scale of your problem. So from length scale, you can calculate what is the value of epsilon. And that value you can use your initial gas as well as the value at the inlet boundary, because you will also need to define K and epsilon as your inlet boundary. I think CFD online also have some calculator where one can use, or one can input some parameters for the flow that you are solving, and it calculates for you what is the value of K and epsilon. Of course, some similar formulas are built up there.
Yes, sir, but that is for some inlet and outlet boundary conditions. But I'm asking like when there is no
Yeah,
inlet.
so you can use because it is just an assumption that what ideally you should know what is the value of K and epsilon in your flow initially. But then we do not know. So and same thing stands for the inlet values for K and epsilon. So you can use the same thing for your flow, and depending on how it evolves, because what you are going to get that with time, how the value of K and epsilon are going to change. So eventually you should be able to get from your equations how the values are changing until you introduce a lot of turbulence, then that may cause problems. So you start with, say, very low turbulence and see how it grows.
Yes, sir. Sometimes what happens, sir, we initialize random values, and what we notice like the solution is not getting converged.
Yeah, so my suggestion will be you start with, say, typically 3 to 5% fluctuations.
Okay, sir. Thank you.
Sir, if the velocity profile is linear in viscous sublayer, so why we need more number of grid points? We can use one grid point at y plus is equal, y is equal to 0 and another grid point at y plus is equal to 5 now.
Well, you can try doing that, and then you can have you make sure that you have sufficient grid points in the overlap layer, because the grid velocity profile is exponential there. You can have two elements here, and then you can have more elements in the overlap layer.
Okay, sir.
Okay, so if there are no further questions, I think we can close the session.
Thank you so much, Professor Raghavendra.
Thank
It was a very informative session, and many students were questioning you, and you have been constantly answering them. So thanks a lot.
Thank you. It's a pleasure to.
Thank you. Thank you.